Okay, in this video I want to talk about improper integrals. Now, improper integrals are, simply put, integrals with infinite bounds. Alright, so you can see one representation of definite integrals is the area under the curve. So indefinite integrals can have the same sort of meaning. They can represent the area under the curve. Okay. Now, when we evaluate integrals that have infinite bounds, you have something that looks like this, the antiderivative from a to positive infinity of a function dx. Now, normally when you evaluate a definite integral, you take the antiderivative and then evaluate that at the bounds, but we can't do that if one of the bounds is infinite. So what we do is we change it over to a limit. All right, so we'll use b since it's the top value that's infinite. We take the limit as b goes to infinity of the antiderivative from a to b of f of x dx, and now I can evaluate that definite integral and then take the limit. Alright, so we can have an infinite bound on the top, or we can have an infinite bound on the bottom. Alright, in which case you simply take the limit for the bottom bound. Or we could have an antiderivative that's bounded on both ends. And if it's bounded on both ends, we can't do a double limit. So you have to find some place in between, well, in between negative infinity and positive infinity, so just some place to break it up so that we only have one bound on either integral. Alright, now improper integrals will either converge to a value or they'll diverge. Alright, so the first example I want to show you is what happens if we compare two of these functions. Alright, f of x is 1 over x squared for x greater than 1, and f of x is 1 over x for x greater than 1. Now, in both of these cases, I'm interested in the area under the curve from 1 to positive infinity. Alright. So my first improper integral gets set up as the antiderivative from 1 to infinity, 1 over x squared dx. And to evaluate this, the first thing we have to do is turn this over to a limit. So I'm going to say the limit, now because it's the top bound that's infinite, I'm going to use b, goes to infinity, of the antiderivative from 1 to b. Now I'm also going to make a little algebraic change here. Okay, this is 1 over x squared, but to evaluate it, I have to make it x to the negative 2 dx. Alright, so this is now the limit as b goes to infinity. The antiderivative of x to the negative 2 is just a power rule, so negative 1 x to the negative 1 from 1 to b. Alright, now that I've taken the antiderivative, I can evaluate the bounds. Alright, so the limit is still there. b goes to infinity. And now this becomes, now again, at the same time, actually, why don't I put another step here? The limit as b goes to infinity. Let's fix up the algebra here. So this is minus 1 over x from 1 to b. Alright, so now this becomes minus 1 over b minus, well, let's write it in, minus a minus 1 over 1. Alright, so this is the limit as b goes to infinity of minus 1 over b plus 1. Alright, and if you recall from Calc 1, if I take the limit as b goes to infinity of 1 over b, I get 0. So this becomes 0 plus 1, which is just 1. Alright, so this limit converges. Alright, and it converges to 1. Alright, that also means that the area under the curve, since that's actually what we were looking for, under 1 over x squared for x greater than or equal to 1 is actually finite, and it's equal to 1. All right, so there's an example of where you would have an infinite bound but still have the improper integral converge to a value. All right, a finite area. If we look at what happens to this one, all right, 1 over x, all right, I set it up the same way. All right, so I have to do a limit, and again, because it's the top bound, I'm going to do b as b goes to infinity of the antiderivative from 1 to b of 1 over x dx. All right, now 1 over x is the antiderivative of the natural log, so this is the limit as b goes to infinity of ln of x from 1 to b. Right. And then I evaluate my bound, so I've still got the limit here. Alright, so this becomes ln of b minus ln of 1. Alright, now ln of 1 is just a constant. Actually, it's 0, but that's still a constant. What happens to the natural logarithm as b goes to infinity? Well, think about the graph. Let me get rid of that. Think about the graph, right? What does the graph of the natural log look like? It looks like that. Alright, so as x goes to infinity, the natural logarithm goes to infinity. So if I try to take the limit as b goes to infinity of the natural log of b, it's going to diverge. Alright, so because the limit as b goes to infinity of ln of b diverges, adding or subtracting any constant to that is not going to make a difference. Alright, so because this limit diverges, the original antiderivative diverges. Alright, so in this case, because we were looking for the area under the curve, the area under 1 over x is infinite. Alright, so we can have either situation occur. Could have a antiderivative that converges to a value, or you could have an antiderivative that diverges. Right? Now, if we have a situation like here, all right, we have a slightly different function. We're looking at negative e to the 2x, where x is less than or equal to 1, and we're interested in the area that's bounded by the x-axis and the function. Alright, so this one has an infinite bound but on the left, so that would be the lower bound. Alright, so I would set this one up as an integral. Now remember, alright, so we're going from negative infinity, that's 1 right there, to 1. Now remember, because I'm below the curve and I'm looking for the area, the x-axis is above the curve, so the x-axis is 0. And then I have to say minus e to the 2x dx. Alright, so that's the integral set up. So now I can take care of my lower bound here. Alright, this is going to be the limit as a goes to negative infinity of the antiderivative from a to 1. Now I can clean all this up in here, and this just becomes e to the 2x dx. Alright, so now we can evaluate the antiderivative. A goes to negative infinity. Alright, so the antiderivative of e to the 2x is going to be 1/2 e to the 2x from a to 1. Alright, so I still have to carry the limit. Alright, so top bound is 1, so that becomes 1/2 e to the 2 times 1, or e squared, minus 1/2 e to the 2a. Alright, now I can take the limit. Now again, 1/2 e squared is just a constant, so that's 1/2 e squared. And now what happens is I let a go to negative infinity. Again, if we come over here, we can see on the graph, alright, as I go to negative infinity, this curve approaches 0. Alright, so if this curve approaches 0, then this is just minus 1/2 times 0, or 0. Alright, so I end up with 1/2 e squared being my area under the curve, and that is my answer for that one. Alright. Now all of these that I've shown you so far have been for areas under the curve. Give you a function, ask you to find the area under the curve. Okay, so if we look at this one is a little different than the last few in a couple of ways. First of all, I'm handing you the definite integral. Since I'm handing you the definite integral, we're not assuming that this is representing an area under the curve. I'm just saying evaluate this definite integral. Alright, so that's the first thing. The second thing is we have two bounds. Alright, so because I have two bounds, I need to split this into two integrals. Now, the best way to do this is to graph the function and find a point that looks good for splitting up your antiderivative. Now, you can graph this on your TI-89, and if you do that, you will end up with something that looks like this. I'm exaggerating it here, but basically it looks like this. Alright, so I'm going to take 0 because that looks like a good place to split it up right there. Alright, so I'm going to do the antiderivative from negative infinity to 0 of x e to the negative x dx, and plus, and then I'm going to do from 0 to infinity of x e to the negative x dx. Alright, so I can do a couple of things to speed along my my process here. I could, if I wanted to, just find the antiderivative of x e to the negative x. Alright, whoops, x squared. Always something. Okay, x e to the negative x squared. Or I could just try and do it all in one shot. I think just because of space constraints, before I turn this over to limits or do anything else, I want to find the antiderivative of x e to the negative x squared, because that'll help me do this a little more quickly. And also give us a chance to review u substitution a bit. So I have negative x squared in there, so I'm going to go u equals negative x squared du equals negative 2 x dx. So negative 1/2 du equals x dx. Alright, so this is now the antiderivative of, alright, x dx, x dx. Alright, I've got x dx right there. Alright, so I can put the negative 1/2 in front, and then I just have e to the u du. Alright, so this becomes negative 1/2 e to the u plus c, which when I sub back in becomes negative 1/2 e to the negative x squared plus c. Okay, so because there's no need to actually go through that twice. It's the same function in both, so I can find the antiderivative first. Alright, so now when I put this together, alright, I have to put together two limits. So I've got a lower bound, so I've got the limit as a goes to negative infinity of the antiderivative from a to 0 of x e to the negative x squared dx. And then I'm going to add that to the limit. Now this time I've got the upper bound as b goes to positive infinity of the antiderivative from 0 to b of x e to the negative x squared dx. Alright, now since I've already found the antiderivative, alright, I can take my next step over here. So I'm going to do the limit as a goes to negative infinity, and that's going to be of negative 1/2 e to the negative x squared evaluated from a to 0 plus the limit as b goes to infinity of negative 1/2 e to the negative x squared from 0 to b. Alright, so now all I have to do is evaluate these two limits. Well, actually I need to evaluate the bounds, then the limits, so let's do the bounds first. So I've got the limit as a goes to negative infinity of, alright, let's see, put in the top one, I get 0, so that means e to the 0 is 1, so I get negative 1/2, and then minus a negative, so that becomes plus 1/2 e to the negative a squared. I'm adding that to the limit as b goes to positive infinity of, alright, so top one is b, so that's minus 1 over 2 e to the minus b squared minus, and again minus a negative, so plus, when I put 0 in here again I get e to the 0, which is 1, so that's just 1/2. Okay, good. Alright, so negative 1/2 is a constant. Okay, 1/2. Alright, now we have to figure this out here. Alright, as a goes to negative infinity, a squared goes to positive infinity, which means the exponent goes to negative infinity. So as I look at my curve, as I look at e to the negative x squared, okay, as x goes to infinity, e goes to 0. Alright, so this becomes plus 0. Plus, now I can make the same argument over here. As b goes to infinity, b squared goes to infinity. E to the negative b squared is going to go to 0. And then 1/2 is just a constant. And I lost a negative sign again. 1/2 is just a constant there. Alright, so I get negative 1/2 plus 1/2, which means I get 0. And again, because I was not looking for the area under the curve, I was handed that definite integral to evaluate. That's a perfectly legitimate answer right there.